Share my screen. Okay, well, thank you, Brandon. I'm honored to give this keynote address. It's a little intimidating for me to follow Jed Rakoff, but I'll do my best. I have a different perspective from him. I'm coming more from the scientific point of view. And what I want to do is really give you the 30,000 foot view, my 30,000 foot view of research in this area over the past few years. And I want to begin with this quote. It's a famous quote. It's probably familiar to many of you. In 1,000 courts at 1,000 places all over the world, witnesses every day affirm by oath mixtures of truth and untruth, combinations of memory and illusion, of knowledge and of suggestion, of experience and wrong conclusions. And this sounds like something that would have been written yesterday or could have been written by anybody in this room. But in fact, it was written over 100 years ago by this gentleman, Hugo Munsterberg. Munsterberg was on the faculty of psychology at Harvard University at the turn of the 20th century. He was hired there by William James. And he's most well known for his ability to take concepts and methods from experimental psychology and apply them to important problems in everyday life. And he wrote a series of essays of that sort, which are collected in this book entitled On the Witness Stand, which I recommend to any of you. The point of this is that if we go 100 years later and look at the things that are written, they're not much different. This is actually a quote from the National Academy's report on eyewitness identification. We conclude that there are insurmountable limits on vision and memory that are imposed by our biological nature and the properties of the world that we inhabit. So the scientific perspective on this has not changed. The question it still begs for an answer, and yet the science has evolved over the years. And so again, that's what I want to tell you about today, that evolution of the science, or at least summarize it. Now, I'm a relative newcomer to this field, and I'm a little concerned that some of you may not have the slightest idea who I am. So my background is, I'm a neuroscientist. I've spent my career studying the brain basis of visual perception, visual memory, and visually guided behavior, which is really interesting work. I've enjoyed it, but I had, in all that period of time, I'd never issued a public statement or offered a professional opinion about the problem of eyewitness identification. I certainly had thought about the problem because I've spent my life studying visual perception. But it was a few years ago that I was asked by the National Academy of Sciences to co-chair a committee for the purpose of evaluating procedures for eyewitness identification. I co-chaired it with Jed Rakoff, of course. It was a terrific committee. I really enjoyed the whole process. And of course, many of the committee members are actually in the room with us today. Brandon, Joanne, Karen. I haven't seen Bill Brooks for a long time. It's nice to see him again. AJ Kramer I saw yesterday. And I see Joe Cecil all the time, but it's nice to see him again. It was a really high functioning committee, and I was very pleased to be part of it. I learned a lot from those people. I also learned a lot from the people who informed the work of the committee, some of whom are in the room with us today. Now, as a result of doing this, I sort of fell down the rabbit hole of eyewitness identification research, and I've yet to emerge, but there are a few things that I remember from the top before I fell down, and one of which is that there's nothing particularly unique or unusual about the eyewitness identification problem, other than the fact that the stakes are very high. These kinds of memory-based identification problems are ubiquitous in normal human experience. Finding your car in the parking lot, your luggage on the carousel. On the lower left is the TSA problem, finding bad things in people's luggage. On the lower right is the radiologist problem, finding bad things in the human body. On the bottom right is the baseball problem, or the umpire's problem, trying to determine whether the runner is safe at second or not. And so thinking about these kinds of problems in conjunction with the eyewitness problem, I've sort of come to, my thinking has evolved to the point where I think there you can categorize different scientific approaches as follows. And for lack of a better set of terms, I'll refer to them as palliative and curative. These, of course, terms derived from the field of medicine. Palliative approaches in medicine are those designed to relieve the symptoms of a disease. Curative approaches in medicine are those designed to eliminate the cause of the disease. And there are lots of examples we can identify in medicine. This is the problem of type 1 diabetes. This is the serious type of diabetes in which the pancreas doesn't make any insulin at all. And so 100 years ago, if you were diagnosed with type 1 diabetes, it was a death sentence. But since that time, we've had a therapy, a palliative therapy, which is incredibly effective and has has prolonged the lives of many countless numbers of people over the years. But we're now to the point where molecular biology and genetics have advanced to where we can approach a curative approach to the problem, which involves genetic engineering such that cells produce the human insulin hormone. What does this have to do with eyewitness identification? How does that distinction play out here? So let me describe the palliative approach, and I'm going to use the word therapy in a rather unconventional sense here. Is therapy in the form of manipulations of environmental and personal factors which improves or affects and ideally improves the outcomes. And what I'm really talking about here is manipulation of systems variables. And this has been an incredibly effective approach to the problem over the years. I'll go through it in just a moment. But what's the curative approach to this problem? And I just as a spoiler, so you're not on the edge of your seats, I'm not going to give you a cure. I'm just going to give you a bunch of provocative ideas. And they start with this, which is that the machine is broken. The machine being the eyewitness. And it's broken because we're asking it to do something that it isn't very well designed to do. And I'll come back to what that means exactly in a few minutes. But let's first consider the palliative approach, because this is the predominant approach in eyewitness identification research. I showed you this slide yesterday. This is just a simple conceptualization of the eyewitness problem. There's input on the left. The eyewitness has a number of variables associated with the eyewitness. These are the estimator and system variables. And the eyewitness, and these really define the operating characteristics of the eyewitness. And the eyewitness produces an output, a decision, and that decision varies in accuracy. And what we want is to know what this function is here. That function relates these variables associated with the eyewitness, these operating characteristics, to the accuracy. Excuse me. It's early in the morning here in California. I got up very early. That relates, this function relates these variables to the accuracy of performance. And so I like to think of this, I think it's useful heuristic, that this is a regression problem. There are coefficients associated with each one of these variables. And for any given case, and we've determined what the optimal coefficients are in modeling this. And there are variables associated with any given case. And I just illustrate them as like these little dials that you can move up and down. And at least some of those dials you can move up and down. The estimator, of course, are fixed, but the system variables can be swiveled back and forth like this. And in doing so, we find that there's a certain set of variables that lead to a certain outcome, a certain decision, which is low accuracy, but another set of variables leads to an outcome with high accuracy. And that's a sort of a simple-minded approach to the problem, or simple-minded way of describing what the approach is. Of course, this is not really, this kind of approach is not new. It's not unprecedented. It's pervasive in other fields of application of science to really applied problems in the real world. This is a prognostic in medicine. There are both diagnostic and prognostic models that can be developed. This is a prognostic model of mortality following head trauma. So there are, it's just a cartoon. There are observations that can be made. These are shown on the left-hand side that are associated with head trauma and based on the coefficients associated with them. Some are important factors, some are less important factors. And there are values that can be measured in each given case, and that is a way of predicting mortality. And this actually has been done. I mean, people have modeled this. This is a published model. And this model here, the IMP-ICDX model, is pretty powerful and one in predicting mortality. A few years ago, my wife was involved in a terrible car crash, and she was in a coma for a couple of weeks. And eventually this team of physicians came to me with these kinds of models and with these, with data on her particular condition and predictions about mortality. And I can tell you from this experience that this is an aesthetically brutalist approach to the problem, but it's incredibly rational. And it's for exactly that reason that this has been such a powerful approach to the eyewitness problem. And I don't need to review for all of you because you are the participants, and many of you are participants in these kinds of studies that have really fleshed this kind of model out over the years. And it's an extremely powerful approach to the problem with a great deal of success, ultimately converging on an understanding of what this function is. Now, that said, I was intrigued when I came across this. This is a book on medical diagnosis, which the authors were inspired to put on the cover in this 19th century engraving, which depicts Plato's allegory of the cave. And those of you who are familiar with Plato's allegory of the cave will know that the premise is that there are a bunch of prisoners who are shackled to the wall of the cave. There are things that happen outside the cave. They can't see that. All they can see are the shadows that are cast on the wall of the cave. And that's their entire lifetime's experiences, those shadows cast on the wall of the cave. And with time, and with experience with those shadows, the shadows become endowed with meaning, with value, with utility, with beauty and joy and sadness. But the truth is they're just shadows. And so to some degree, I worry a little bit that we're sort of looking at shadows here and trying to make something of it. And we have to be careful about it. But as the research proceeds, I think we'll find that the shadows begin to take on important meanings. There is, again, in the allegory, some of you will remember that there's a part of the story involves one of the prisoners being freed, and he goes out into the real world and he finds out what the causes of those shadows are, what's actually casting the shadows on the back wall of the cave. And he comes back to tell the rest of the prisoners. It doesn't end well, but this knowledge of the causes leads me to the other approach, which is the curative approach, that is understanding what causes eyewitnesses to fail. And my argument, again, is that the machine is broken. It's broken because we're asking it to do something that it isn't well designed to do. Well, what exactly does that mean? That's a strong, rather provocative statement. My argument is based on this axiom. I think this is axiomatic because there's a lot of evidence to support it at this point, which is that people are far better at making comparative or relative judgments than they are at making absolute judgments. And there's lots of theoretical and empirical evidence to support this, dating back to the middle of the 19th century with Gustav Fechner, Louis Thurstone in the early part of the 20th century, Duncan Luce, mathematical psychologist, in the later part of the 20th century, and lots of empirical studies that support those theoretical formulations from those guys over the years. There are also interesting theoretical perspectives from evolutionary psychology. And I'll certainly admit that evolutionary arguments are just so stories sometimes, but it is true, or the evidence suggests anyway, that survival and the ability to reproduce depend heavily upon comparative or relative judgments about, over the course of human evolution, about things in our environment, as opposed to absolute judgments about things in our environment. So there is an argument that there's been a selective process for this ability to do comparative judgments at a high rate, unlike absolute judgments. So that's an axiom that I start with. Here's an observation, which is any of you can make this observation. The traditional eyewitness lineup task demands an absolute judgment. That's the guy, that's an absolute judgment. And here's a deduction based on this axiom and this observation. which is that traditional eyewitness lineups place impossible demands on the machine. And this is hyperbole, of course, for dramatic effect. It's not quite impossible, but it makes it very hard for the machine to cope with this kind of problem. So let's come back to the machine here. The eyewitness is an information processing device. People don't tend to think about it this way, but that's necessarily true. And as I said yesterday, information processing devices often have two stages of processing. There's measurement and there's classification. And this is characteristic of a good fraction of normal human behavior. We do things, is the fruit ripe? Is the turkey done? Is this where we turn left? Is that Wagner or is that Strauss? Is that the smell of gardenia or jasmine? And so on. And we've also populated our world with information processing devices that have these two stages incorporated. I gave you a couple of examples yesterday. The smoke detector in your house is both a measurement and a classification device. And there's this machine I've always been fascinated by that they have at the grocery store, where you take all your spare change and you dump it into this thing, and it nicely measures the sizes of the coins and classifies them based on those measurements and puts them into these neat little rolls. And again, there's lots of these kinds of things, and probably the device that most of you are most familiar with of this sort is this one. And this is an Apple product. The same principles apply to any other smartphone that uses Face ID. And the Face ID property of this phone is something that's been extensively developed by the engineers at Apple. And there's a lot of fancy electronics behind this, but we can look at it strictly from a signal detection point of view, which is illustrated in the next slide. And the iPhone is making an absolute judgment. We're asking it to say, is this Tom? And what's plotted here, and this is important that you understand this, this is a plot of the probability distributions for measurements of Tom's face versus everybody else's face, or all faces that are not Tom's face. And of course, it's just a cartoon. But what this means is that for any given value that's measured by the iPhone, by the camera, there's a set of values that correspond, that can be documented, validated to correspond to Tom's face, and a set of values that can be shown to correspond to everybody else's face. And this axis here is the probability, or you can think of it as a frequency measure on the y-axis. And so you can see the problem here is that these things overlap. They overlap significantly, which means that there's a whole bunch of values that the iPhone can measure that we can only say probabilistically whether it's Tom's face or it's somebody else's face. And yet this is really important that the iPhone do this correctly. And so given these data, these are what's called the decision variables. Given these decision variables, the engineers at Apple, and this is based on normative values, the engineers at Apple decide to put the classification criterion here, the decision criterion here, because we don't want any type 1 errors. We don't want any false positives. I really don't want my phone to open up for anybody else's face. And with that, I have to accept the fact that sometimes my phone is not going to open up to my face. And that's okay, as long as nobody else's face can open my phone, because that would be bad. So they place this criterion at a pretty stringent level here. So the likely, anything that exceeds that value, the phone says, all right, it's Tom, let's open up. And that works really well. And we have a nice, transparent understanding of the signals that are involved and the classification criteria that are applied. Now let's suppose that the decision is being made not by the iPhone, which we understand completely because we made it, but by the human observer, the eyewitness. And the eyewitness's task is the same. The eyewitness is forced to say whether it's Tom or not. This is an absolute judgment that the eyewitness is making. And the same logic applies. The problem here is that we don't know what the classification criterion is. We don't have that information. It's inside the witness's head. It's not accessible to us, unlike in the case of the iPhone, where it was engineered from scratch. We also don't have, and this is an even bigger problem, we don't have any idea what the underlying decision variables are. in this case. All we have is an assertion that it's Tom. And the question you have to ask yourself is, can you believe that? Does that make any sense, given that you have no knowledge of the underlying causes of that decision? This is a problem. And I mentioned this problem yesterday. I showed you the slide yesterday. Again, the problem has to do with the fact that the measurement and classification systems are built into the brain, and we can't get in there, and we can't see the transference of information from the measurement stage to the classification stage. There is no transparency. There is no independent audit of the measured values. There's no means to calibrate the measurement device. There's no independent assessment of the relationship between those measured values and the classification criteria. And so this is a problem. This is a problem because, again, this is all we have. So what we need to do is get access to those measurement values. That's number one, because we know the human brain is capable of making those measurements, and we need to cut the eyewitness out of the classification, because the eyewitness's criterion is inaccessible to us. It can be controlled only to a small degree, and the best thing to do is just cut the eyewitness out. We use the eyewitness, therefore, as a measurement device. That's what the eyewitness is good for. Well, how do we get those measurements? They're inside the eyewitness's brain. Neuroscience, and these are the measurements, of course, that we want to access. Neuroscience has advanced by leaps and bounds over the past 50 years, and you might suppose, well, we can go in and, with physiological means or using an MRI machine, measure stuff from the eyewitness's brain and get access to these underlying decision variables that are important for the decision the eyewitness has to make. And then we can make an independent decision based on those. Again, cutting the eyewitness out of the classification stage. This is not going to happen. It's not going to happen, and certainly in our lifetimes, and I have some doubts about whether it could ever happen. It's a really difficult problem. But there is a solution to this problem, which is, again, going back to the point I made earlier that's suggested by this axiom, which is that people are far better at making comparative or relative judgments than they are at making absolute judgments. And so let's suppose we make this a relative judgment task rather than an absolute judgment task. And the way to do that was, I mentioned this yesterday, was advanced by this man. This is Louis Thurstone from almost 100 years ago, who promoted the idea of perceptual scaling by paired comparison. And this is a technique that's been abundantly used over the past 100 years for lots of different applications, which involve judgments of human observers about quantities in the real world. And probably the example that most people are most familiar with is this one. This is perceptual scaling applied to the practice of optometry. Those of you who have myopia and go to the optometrist, and that's probably just about everybody, what you do is you go in and you sit, they put this big thing in front of your face, it looks like that, and it's got a bunch of lenses in it. And the goal, what the optometrist is trying to do, is identify the refractive correction that overcomes your myopia. That is, to give you the sharpest possible image. And so how do they do that? They don't simply ask you what the best lens is, because that's a hard problem. What they do is they show you two lenses, one after the other. And if you've been there, you know the refrain. The optometrist says, which is clear, number one or number two? Number one or number two? I say number two is better. Which is clearer, number one or number two? Number one is better, and so on. And they do a series of these presentations in pairs. And as a result, and that's what's illustrated here, a series of these in pairs. And as a result of those paired comparisons, it's possible to reconstruct the merits, if you will, or the measured values of a lens relative to the goal of perfect refractive correction, which is shown here. And so that's how the problem works. That's the solution to the problem in the field of optometry. I'm sorry, there's a jet plane flying over my head right now. There's a big military base just to the east of us. But that's the solution to this problem in optometry. And we thought, well, maybe we could apply this same approach to the eyewitness problem. That is, we show these people in pairs, the same number of people. Well, it doesn't really matter how many people are in the lineup, but we chose 6, and we showed them in pairs as 15 possible pairs. And we simply say which face looks more similar, in this case, which looks more like Tom. It's a relative judgment. It's not an absolute judgment, and it has the merit, therefore, of being a simpler type of task for people to perform. And the way to think about it in signal detection terms is the following. Again, this is on the y-axis is the probability of a particular measure, and the x-axis is the measurement. And so we have measurements from Tom's face and faces that are not Tom, and you're asked to say which face looks more like Tom. And the decision criterion is not a problem in this case, because all we have to do is put the decision criterion right between the 2 distributions. All we have to say is which of these 2 looks more like Tom. And we're not asking you to say, is this Tom? Which one looks more like Tom? And we do that repeatedly for a bunch of different measurements of faces. And by doing that, we gradually reconstruct the underlying distributions of decision variables for Tom's face versus everybody else's face. This is what we want. This is the grounds for making a rational decision. And at this point, we're done with the eyewitness. The eyewitness doesn't have anything more to contribute to this problem, and we bring in the statistician. And yes, Karen, I know more than one statistician, maybe 2 or 3, but you're the best. And we bring in the statistician, and the statistician says, well, what's the problem you're trying to solve? And we tell him, and the statistician says, well, this is a technique you should use, and this is where you should place your decision criteria. And we chose to use a simple signal detection analysis. There are lots of other procedures you could do. As Karen pointed out earlier, this is a binary classification problem, and there are many techniques that could be used to solve it. But the point is that the statistician is going to apply the most objective, the most rational approach to the problem, which is something that the eyewitness, who is personally invested in the problem, cannot do. And so we take that out of the hands of the eyewitness. And this is, of course, what we did in this paper that was published a few months ago. And in that paper, again, we measure the recognition memory strings using the procedure that I just described. We use a statistical analysis, and we come up with some measure of accuracy for the decision that's generated by those means. And so I want to come back now to this distinction. These are 2 very powerful alternative and I would say complementary approaches to the problem. The palliative approach has been enormously successful. It's tried and true, as you might say. And I think we just have to keep plugging away. And I've heard enormously exciting things at this conference along the lines of this kind of approach. But at the same time, I think that we need, like the prisoner who went outside of the cave and came back to talk to the shackled prisoners, we need a curative approach. That is, we need to start looking at from the bottom up, what's going on with the eyewitness and what's the best way to ask the question. And I'll end with that. Thank you very much.